Hey, we're going to talk about some of our applications for derivatives. We'll kind of go through these in different stages. But first, I want to kind of remind you of a couple of things. We talked about when a function was increasing in the past, and that would be when it's going up. And if that's the case, it has a positive slope or positive rate of change. We also talked about when a function is decreasing, it has a negative slope or a negative rate of change, and that is when it is going down. So we looked at different graphs and we talked about the intervals of increasing and decreasing. The derivative of a function gives the slope at a point. So we've been taking derivatives long ways with limit definitions and with the shortcut definitions as well. But we know that if we have f of x, that is a position, that tells us the y, and we know that f prime, the derivative, tells us the slope. Okay? And a slope of 0 infers a flat line. So we can either think about a horizontal line in the case, or we can talk about just at a point where the tangent line would be flat and have a slope of 0. Okay, so a slope of 0 infers a flat line or a flat tangent line. Now, how is that helpful here? Let's slide up the page, see if it works out for us. Okay, maximum minimums. So for a continuous function, that means we don't have to pick up our finger or pencil to draw the graph. To stop going up and start going down, the slope must change from positive to negative by going to a slope of 0. So what I'm saying here essentially is if a function is going up, increasing, and then wants to go down, it must go through a place where it has that slope of 0, as I just kind of drew out up there. So there's the slope of 0 I had before, but this is a positive and this is a negative on the other side. So we'll have a maximum. There's different types of maximums, but we'll have a maximum if we're going up, stop going up, and then start coming back down. And likewise, we have a minimum if we're going down and then turn around and go up. So if we're going down, that's a negative slope. We'll go through a slope of 0 to have a minimum. And then we'll have a positive slope so it can start going back up. Okay, so we're looking for maximum and minimums eventually based off of where a slope is 0, and remember that our slope being 0 means our derivative is 0. So let's kind of read this graph right here for a moment. So looking at this graph as we have it, we could say that up to about -1, this thing is decreasing. So I'm just going to try to draw a line right here. So over here it's decreasing, which means it has a slope is negative. It's going down. And then somewhere in the middle here, and I don't think it's exactly where 0 is, there in that position it's increasing. Between here is going up, so it has a positive slope. And what did we have there? It was going down, it stopped going down, and then it started increasing. So let's kind of make a dotted line here so that we can do it. But it started increasing after it went down. So this is a minimum. It goes down, it goes up. So that position right there has a slope of 0 where it turned around. And here from 0 over to about 2, we're looking at, I'm just breaking this up so that you can see, in that area we're decreasing, going down, so slope is negative. And as you see there, we went from a positive slope to a negative slope. That point right there has a slope of 0. And it was going up, then down, so it flattened out to change. And then on the other side of 2 over here, we have an increasing slope, it's going up, so the slope is positive, but we have that low point where it went from negative slope to positive slope, and right there that is a turning point where it can turn around. The slope is 0. Okay, a couple of terms down here we may or may not use very much. These usually come from the traditional calculus, but critical points are where the derivative is equal to 0, and that would happen anywhere the slope is 0. So on my graph there's 3 places where the derivative would give us a slope of 0. And these are potential turning points. Now, just because the slope goes to 0 doesn't mean it has to turn, and we'll run into that later on if need be. But this is where it flattens out and can turn. Okay, some kind of neat things here. We have relative maximums. This means a point higher than the points directly around it. So based off the graph I have up above here, let's get something I can write with. That happens, the relative maximum here looks like it happens at about 0, 1. It's higher than the points around it. Okay, so it's coming up, it goes down. That's what I was talking about, a maximum. Now if we look down here at absolute max right below it, the highest point of the function, on the ends of this function it keeps going up on both sides. So there's not an absolute max, there's not a definite highest point. But there is one that's, like we said, the relative max at 0, 1, where it's higher than the points around it. So it's higher relative to the points around it. It's maximum compared to what's close by. But as far as an absolute max, it doesn't have an absolute max. Relative min, that's just lower than the points around it. So that happens over where we had this min. It looks like negative 1, 0. It's lower than the points around it, lower than the points on the left and the right. And over here at what looks like maybe 2, 5. So we can have more than one relative min, just like we said both of these are low points. The graph was going down in both places and then it continues to go up after that. Absolute min would be the lowest point of the function. So while there's 2 places here that are lower than the points around them, one's at negative 1, 0, and the other one's at 2, negative 5, sorry. The 2, negative 5 is the absolute. So based on the graph, there's nothing lower than that. So technically, the absolute minimum is negative 5 because that's the lowest it ever goes, but I also give the position where that happens. So it happens when x is 2, and it gives us a negative 5. Okay. And just another note here from traditional calculus, and it may kind of come into play for us when we define a function. If a function has endpoints, and those endpoints could be maximum or minimums. So it could be that if we had a graph, and I'll just draw a little one over here, that depending on how the graph is defined, maybe if we make it start at A and end at B, so it doesn't go on forever, those could be the highest or lowest points of the graph. So they're not really the critical points that we think of as where it turns around or where it goes flat. But if we were trying to maximize profit, we wouldn't necessarily want this point that I've got way down here, because there is a higher point over here within our domain. Okay, so just things to think about. We're not going to be graphing all these right now, and we're not going to be looking this deep, but it is the sensibility behind what we're doing. We're going to be trying to find maximum minimums of functions, usually for applications. And the main thing to take away from this discussion is we're going to take the derivative so we can locate where the slope is 0, so we can tell where things would turn around and have high points and low points. So that's our big takeaway.